there are many addressable memory locations in each computer. So in this video, we're going to talk about pointers and their properties. This new concept, pointers, have many uses in C and also in C++. Besides being very efficient method of assessing data, pointers provide efficient techniques for manipulating data in arrays, in passing data from one end to the other, passing by address, that said. So we're going to look at how we declare and define pointers properties, how we manipulate them, and things like that in this video. Let's talk about what a pointer is. A pointer is the data type. It is also a variable that contains an address that can be used to access data. Let's say, for example, right, we have this integer, and this integer is called integer I, and this integer is located right at a memory address. Let's say 0 times FA, right, 1. Now this memory address is located right in a vast memory cloud right inside your computer at runtime. At runtime, we can have a section called stack, another section called heap. Let's just say for the purpose of this discussion, memory is coming off of stack, right? And this is a stack memory. So now this integer I, when declared, is going to have a memory location right here. Now, you may have a pointer, which is another variable. Let's say this pointer is integer start P, right? Now, this pointer may have an address associated with the address of your I right here. And in this case, we say %I. We'll talk about this also later when we define and declare these in the next sections. But suffice to say that this P now has this memory address of 0 times FA1, right? So P's value is actually the address of someone else. So this is integer I's memory address. Now, with that established, notice that this pointer, right, which is a variable really, and variable could be assigned with a different value at runtime, unless we make this entire pointer a constant. Now that's not the case, but pointer can also be constant. So if a pointer is a constant, it could also have a memory address that which cannot be changed, right? Because the variable being a constant, it is a read-only variable and not a variable where you can be altered or changed at runtime. This pointer itself, which is P, right, also has another memory address, right? 0 times, let's say, K2, right? Now this is saying that even though P, which is a pointer, right, has a value that is someone else's memory address. Now P is also a variable sitting on the stack, right? So maybe this memory address is somewhere here, right? This dot right here is where P is. So that you can have basically these pointers and integer, strewn all over the places on stack, each having its own address, right, at runtime. Here we're saying an address and expression, right? One of the expression types in the unary expression category consists of an ampersand and a variable name. So if we do ampersand and a variable name, right? So what this is saying is this ampersand is address of, right? Literally, you can translate it in English, right? This ampersand, when sitting in front of a variable, address of. Now, this address of pulls the address, right? Fetches the address of I, right, at memory location 0 times FA1 right here. Now, this ampersand is a unary, right? Remember what a unary is, it means 1, right? Expression means something that could be evaluated into a value, right? So this unary expression, namely the ampersand, gives you the memory address, right? Or in this case, we can say the memory address of, right? What? Of I, right? Okay, so that's what this is saying. The address expression makes use of this ampersand. So in general, the address expression, when used on top of a variable, has this convention, right? Variable name. Okay, so what if this variable name is? This entire expression evaluates to a memory address, right? Ampersand variable name. This demo illustrates having two, right, variables that we declare on the stack, right? So it depends on your computer and the memory footprint. Every computer is different. So when you declare variable like this, A and B, they're sitting somewhere here. Let's say this is A. Let's say this is B, right? So if you do this, right, on different computers, you'll be getting different memory addresses for A and B respectively. And even on the same machine where A and B does not have to be sitting next to each other, but most of the time, right, in the experiences, let's say if you don't have a lot of stuff running on your computer, if you do this decorations, one after the other and simply just run this entire program at runtime, most likely they're sitting next to each other. So if A has the memory address of 142300, B could be sitting next to each other, meaning incremented by 1. Sometimes the memory just goes down, right? So you don't have to have, one being 300 and the other 301. The other one could be 299, right? So whether the memory goes up or down is depending on your operating system, right? We also have, big Indian and small Indian machines. So they have different memory footprints in general. And note that these memory addresses, these are integers, right? When you, let's say, turn this, right, into a hexadecimal, right? So I'm making this up. So this might have 0 times FA1, right, or something like that. But just note that memory address is an integer. Regardless, this is expressed in a decimal system like here, or hexadecimal, right, like so. For most data type in C, C++, the very first byte, right, of a variable is where its memory address is. Since char is only 1 byte, this entire 1 byte has a memory address associated with the location of A and B. So for example, if you were talking about an integer is 4 bytes in memory space. There are actually 4 slots right here. And the very first slot is reserved for the memory address of this integer. Let's say this integer is I, then this is where the memory address, right, is stored inside of here. So for the char, that only 1 byte that is associated with this area will be used basically to store the memory address. So for a char, right, its memory address will just be stored in that 1 byte memory storage reserved for that char at runtime. We're printing, right, these 2, right, addresses are, notice that this ampersand is a unary expression we're talking about, address of, right, address of A, addresses of B, respectively, right, one at a time with a new line at the end. And notice that the format specifier here uses P, right? This percentage sign P represents pointers. So you got to use this to print out the value of A and B. So this is what we're getting. Now, if you run this multiple times, you'll see that these memory addresses changes from time to time, right? So there's no telling as to, at runtime, which memory storage, right, would be used to store these variables A and B. This is the reason why, since memories are dynamic, right, and they varies from computer to computer, you always get different numbers. But generally, they could be, sitting next to each other, as is illustrated here in this example. Right, so we just went over this, right? If we have an integer, we have 4 bytes, right? Char is 1 byte. Now we can also have float, right? Or even a long, right? And this could be 8 bytes, right? Now, let's say this is the size of your memory. 1 byte is really small, 4 bytes, half the size of your long, right? Right here. Now the very first byte, right, which for char is 1 byte, basically its entirety. For long, the very first byte is where the memory address, right, this address is stored. Let's say if you have an integer I, char A, and then long flow F, right? Its very first byte is used to store the memory address MA here. So that's generally what happens, at runtime. This is runtime. Okay, so what does that mean by runtime? Every time you hit run, right, in your IDE for the program that you wrote, you are essentially at runtime, right, after you start running the program. And that's what happens. The memory address stores in it. And memory address is the hexadecimal number, which is an integer. This one illustrates an integer, right? So we have integer I, right, that we're declaring, let's say at runtime. And then what happens is, right, your compiler reserves 4 bytes memory space. This is 4 bytes. Why? Integer is 4 bytes. Let's say this integer is A, okay? Since we're saying it here. And this one integer A occupying 4 byte, and this one has the memory address this. At some point, we also say, and since they're sitting next to each other basically, and we have it like this, right? Okay, so this is line, let's say 1, this is line 2. Now line 3, right? You may have A equals, right, minus 1, 2, 3, right? And then this is a statement, so we evaluate this. So basically at line 3, we assign a value of negative, right, 1, 2, 3 to A. And then line 4, we have B equals 1, 4, 5, right? So this means that we're assigning the value of 145, right, to this integer, sitting at 2, 3, 4, 5, right, 6, 4 memory address. So this is a memory address, which is stored as a part of your 4 bytes integer space, right? That's the memory address. And then the other 3 bytes is reserved for 145, right? And same thing with A as well. So this illustrates integer constant and variables here. So remember this constant, this means literal. So literally you're assigning a constant value, right, to be the value of A, and another one for the value of B. That's what this is illustrating.